Hello everyone, this is Kyle Goodrich, the president and founder of TCarta. Today I'm going to speak on a new space-based standard for remote bathymetric surveying. This presentation was initially intended to be given at GeoWeek in Washington, D.C., but given the cancellations, I'm going to give it online. I've cut the material down a bit. I'm going to go fairly quickly, so if you have any follow-up questions, please feel free to email me afterwards. Here's a statement of 25 leading hydrographers on the quality of data in their industry and how to define it. Given the lack of international standards for satellite-derived bathymetry, we must come up with our own ability to communicate the quality of data to our end users. Now, to do so is a bit of a challenge because often satellite-derived bathymetry is deployed in an area remote and inaccessible locations. These are typically where no in situ measurements are available to validate or to speak on the accuracy of our data. We have a variety of different ways we can approach this, but they all kind of have their shortcomings. Apart from the sixth one here, an independent sensor, which I'm going to speak on today, that to help validate our optically derived satellite-derived bathymetry. So there remains a need for a globally applicable mechanism for communicating and calculating the accuracy of satellite-derived bathymetry in order for it to be wider used within the industry. Now, ISAT-2, a NASA satellite, and the green space-based laser can provide this solution, and a scalable, deployable software tool developed by TCarta can make this accessible to many people. The ISAT-2 mission was launched in 2018. It's a 3 to 7 year long mission to map the sea ice, elevation, and tree canopy primarily. Now, the fact that it measures seafloor bathymetry is a bit of a surprise, but it's doing a tremendous job of deriving water depths. The satellite's mission will go across the entire Earth. This is 1 day's global collection in the lower left, and then 8 cycles of imagery over Hawaii in Pearl Harbor. So it shows that it's collecting ongoing data for validation that we can use for validation. Now, TCarta, partially funded by the National Science Foundation Small Business Innovation Research Grant, has developed an easy-to-use software tool to access ISAT-2 data, clean the data up, correct it for refraction, and export out a cleaned bathymetry profile. But so now we've been able to prove that we can do this globally. The sensor produces good coastal bathymetry. It does collect data in an ongoing way, and TCAR has developed a simplified data access, but we don't know if it's accurate enough to use to validate satellite-derived bathymetry. Just because it's a depth doesn't mean it's a good depth, so we need to validate the space-based laser. So that's what TCAR has done. We developed a number of global evaluation sites. These sites were chosen based on areas where we had good in situ data to get a good understanding of how the accuracy of the ISAT-2 bathymetry data. I'm going to zoom in on a couple of these fairly quickly here. Here's Perth, Australia, a classic place to evaluate satellite-derived bathymetry. And here we are comparing ISAT-2 transects to aerial LiDAR data, and with a mean average error of about 40 centimeters. And as you can see in the elevation profile on the lower left, each of these examples is going to have an elevation profile and a scatter plot of the comparison between the in situ measurements and the ISAT-2 data. But you can see here in the elevation profile on the lower left that they match up quite closely. And these little points that are dangling down here in the scatter plot, we later determined those are actually an area of infilling, an area where sand was harvested from the seafloor and was later infilled. Next, we are in the Florida Keys. We've compared this data against the aerial LiDAR from the U.S. Army Corps, and it's also coming to about 40 centimeter average error from the aerial LiDAR. And now we're in a remote island in Saipan, where we've compared it against multi-beam data as well as LiDAR. As you can see in the elevation profile on the lower left, we catch the bottom of the channels at about 12 meters deep. The deepest we reached in this area was about 29 meters from a space-based laser. So it has a good ability to map depths from about 0 to 30 meters of what we've been seeing from these trials. Now here we're going to use the ISAT-2 data to validate our satellite-derived bathymetry. We've produced a worldview-derived bathymetry surface, using a multispectral process, and then use the ISAT-2 data to validate the multispectral bathymetry. So now we've used 2 space-based sensors, one a passive sensor, WorldView 2, WorldView 3 in this case, and then we've used an active sensor, the ISAT-2 satellite, to validate them. And the accuracy average error is about 35 centimeters between the two. Now, the ISAT-2 coverage is a bit limited in the Arctic here due to ice cover, and we had to capture transects that were only during the summer months when there's open water, which were few and far between, but we managed to capture a few here for comparison. So what we've done here is proven that ISAC provides a globally applicable space-based bathymetry mapping capability and provides a tool that we can substantiate the good quality data of our satellite tribathymetry, trying to speak to that hydrographic community statement on how to validate data. And then also provides this universal standard for deriving speaking to the quality analysis of satellite tribathymetry. And furthermore, we're continuing to do hydrographic community participation in helping us determine, further evaluate the evaluation of this data.